Hello, this is Stylianos. I'm a physics teacher with ATS, and in this video we'll try to solve the second question from the 2023 AP exam for electromagnetism. This is a question about the electromagnetic induction and Faraday's law, but it also includes a few parts from the topic of electromagnetic forces. What we have here is a loop that is made by a resistor, two rails and a conducting bar, and there is a magnetic field. And as you probably know, time is essential for the AP exam, so I try to avoid reading the questions. I try to actually scan them and I try to quickly see what are the elements of the question. The diagram is very, very important to understand what we actually have on the diagram: resistor, moving conducting bar, magnetic field, a spring. We're going to see how we can use them and quickly scan the question. In this question we have values that we will need to use, and he tells you that we release the bar from rest, then we lose contact with the spring and the bar moves to the right, then later it enters the first magnetic field, it enters the second magnetic field, and then there is no magnetic field. We're going to see about this, and quickly the question is to find the force exerted on the bar at time B, and time B is between time 2 and time 3, so when it is on the first magnetic field. There are two ways to answer this. The fast way, we'll see it in 2 minutes, and the question that takes a little bit of time is by trying to see what is happening. Since the bar is moving in a magnetic field and the area of the loop increases, this increases the magnetic flux on the loop, and this induces a current. In order to find the current on the bar, we are using the right-hand law, where the speed is the thumb, the magnetic field is the 4 straight fingers, and the direction of the induced current is the open side of the hand. So what we have is the magnetic field into the screen, the bar is moving to the right, and this means that there will be an induced current upwards. Since there is an induced current upwards, the magnetic field applies a force on this bar, an electromagnetic force, on electric current carrying wire. And again, the direction of the force, we will find it with the right hand law one more time. In this case, the thumb shows the direction of the current, the 4 straight fingers are into the screen, and there will be a force to the left. So we answered part A quite fast. There will be a force to the left. The fastest way to actually apply this is that this electromagnetic induction happens because there is an opposition. The loop is opposing to the change of the magnetic flux. So since the change of flux is happening because the bar is moving to the right, the loop opposes to that. So by Lenz's law, there will be a force that opposes the change of magnetic flux. So there must be a force to the opposite direction that causes the change of flux, so there will be a force to the left. We can continue to part B, and the first part of part B is to calculate the magnitude of the current in the bar. We cannot find directly the current in the bar, but we can try to apply Faraday's law, which states that the EMF is minus number of turns for the loop, change of magnetic flux divided by the time. The magnetic flux is B times A, so change of magnetic field multiplied by the area divided by the time. Now, in this case, the magnetic field does not change. What changes is the area, but the area is length multiplied by width. Length times width divided by the time. Now, we need to also check the diagram. The length of the bar does not change. What changes is the width as the bar is moving to the right. So I can say number of turns, BL, change of width divided by time. But the change of width divided by time is actually the speed of the bar. So the EMF is minus number of turns BLV. We have one turn, the magnetic field probably will be given somewhere, 0.5. The length is, I saw it somewhere also, 0.4. And the velocity is 2.5. This is 0.2 times 2.5. This is 0.5 volts. The minus is not really important in this case. It just shows that this EMF is opposing the change of magnetic flux. We check the question, we need to find the current, and we quickly say that the magnitude of the current is EMF over the resistance, 0.5 over the resistance also was given somewhere, 0.3, and this is 1.67 ampere. And also we can find the force on this bar. This force is the force by a magnetic field on an electric current carrying wire. So this force is equal BIL, and this is the magnetic field again, it is 0.5, the current we found it 1.67, and the length was 0.4. I believe that this will be, this is 0.2 times 1.67, so it will be around 0.33 Newton. And we can continue to tell something about the speed of the bar as a function of time until we get to time 4. The bar started from rest, and the reason why it starts moving is the force by the spring. So the speed will be increasing. However, because the because the force by the spring is not a constant force, we will not have the increase of the speed linearly. So the speed will increase in a non-linear way, and it will tend to become constant when the object is about to leave the spring, is about to be detached from the spring. Later, after it becomes detached from the spring, after it loses contact, it just slides to the right. Now we need to see if we have friction or if he tells us something about this. Now we can assume that there is negligible friction. Yes, frictional forces are negligible. So after it loses contact with the bar and until it enters the magnetic field, the speed remains constant. And later there is a force to the left, and this force will tend to decrease the speed. Now we need to determine if the speed will be decreasing linearly or non-linearly. In order to figure this out, we say that the force depends on the magnetic field, which is constant, the length that it is constant, and the current depends on the EMF, and the EMF depends on the speed. But since there is a force to the left, the speed will be decreasing, so this force depends on the speed, and the speed is decreasing, so this means that the force is changing. So there will be a non-linear change of speed, so somehow like this, a non-linear change of speed. Now, a little bit careful, when the bar enters the second magnetic field, what changes is the direction of the current. So a change of magnetic field and at the same time a change of the direction of the current keep the force into the same direction. So the speed will keep decreasing, and it will tend to become zero. So the graph approximately looks like this, with a non-linear change. Maybe I should make it somehow like this, a non-linear change. There should be a curve. And we continue. that there is a new resistance now on this loop, and we need to find the total resistance. In this case, we can clearly see that the two resistors are connected in parallel, so the equivalent resistance is 1 over R plus 1 over R to the power of negative 1. This is 1 over 0.3 plus 1 over 0.3 to the power of negative 1, so 2 over 0.3, and if we flip it, 0.3 divided by 2, it is 0.15 ohms. And I think this is what we actually need. And in the original scenario, the magnitude of the acceleration is A original. Okay, in the new scenario, there is a new acceleration as it is about to enter, and we need to figure out if the new acceleration is more or less than the original acceleration. As we remember, this acceleration depends on the force and the mass. The mass stays the same, but the force is equal Bill. And the current is EMF over R. So since the R from 0.3 it becomes 0.15, the resistance decreases, and this means that the current, or actually the acceleration, should increase. This means that the acceleration nu will be greater than the acceleration original. And one more part, we need to describe a possible modification for mass, magnetic field, or length that will result in a smaller potential difference and when it is about to enter the first magnetic field. And we said that the potential difference, it was blue, it was BLV. So a possible modification that can decrease the potential difference is a smaller magnetic field, or bring the rails closer together, a smaller value for the length. Now regarding the mass, I'm not sure that it plays a part, but we can say that the mass plays a part on the acceleration of the rod. So since the rod, if we change the mass, this will change the acceleration, and the acceleration we want a smaller potential difference, so we need a smaller acceleration, so probably we need to increase the mass in order to produce a smaller acceleration, and a smaller acceleration will actually bring a smaller EMF. So from this we need to actually select only one part, so smaller magnetic field will just reduce the value of the induced potential difference. I think this is done, so let's recap for a few minutes. We need force by magnetic field on moving rod. This force opposes the motion of the rod. Faraday's law for calculating first the induced EMF and then the current on the bar, and also force by magnetic field on long current carrying wire. Then, in my opinion, this is the hardest part, that the speed increases, remains constant, and then it decreases non-linearly. And the resistance for actually we have an electric circuit, two resistors in parallel, what change does this bring to the acceleration, and how we can decrease the EMF.